In this lesson, we will derive the conservation of energy equation for control volumes. Often we want to know how much energy is required for a process to occur, or how much energy can be extracted from a device. For example, how much power is required to pump water from one storage tank to another? How much power is required to create a sustained 30-foot high jet of water from a nozzle in a fountain? How much power can be extracted by a steam turbine in a coal-fired power plant? These questions all involve energy and can only be answered by applying the conservation of energy equation. Here we have a mass shaded in pink, which we will call our system. The system has a total energy E_sys. Two types of processes can affect the energy of the system. Heat transfer is the exchange of energy between a system and its surroundings due to differences in temperature. There are three modes of heat transfer: conduction, convection, and radiation. We will denote heat as capital Q, and the rate heat is transferred to or from the system as Q dot. Work is the exchange of energy between a system and its surroundings due to other factors such as the movement of boundaries, flow of electricity across boundaries, flow of mass across boundaries, and other sources. We will denote work as capital W, and the rate work is transferred to or from the system as W dot. The first law of thermodynamics for a system states the time rate of change of a system's energy, dE_sys dt, is equal to the total rate of heat flux into the system minus the total rate of heat flux out of the system plus the total rate work is transferred into the system minus the total rate work is transferred out of the system. The summation symbol is used in front of Q dot and W dot because there are potentially many sources of heat and work transfer. Capital D is used in dE_sys dt to emphasize that we are taking the system point of view. The right side of the equation can be rewritten as the net rate of heat transfer into the system, Q net in dot, plus the net rate of work transferred into the system, W net in dot. Let's imagine a control surface, indicated by red dashed lines, surrounds the system at this moment in time. The control volume is contained inside of this control surface. At this time, the net rate of heat and work transfer into the system is equal to the net rate of heat and work transfer into the control volume because they occupy the same region of space. We now apply the Reynolds transport theorem with the extensive property capital B being the total energy capital E, and the corresponding intensive quantity lowercase b being the specific energy lowercase e. The specific energy is the total energy per mass. Plug in the total energy for capital B and specific energy for lowercase b. We previously stated that the left side of the equation, dE_sys dt, is equal to the net rate of heat and work transfer into the system, which is also equal to the net rate of heat and work transfer into the control volume. Putting everything together, we have the conservation of energy equation for a control volume in its most general form. The time rate of change of energy in the control volume plus the net flux of energy through the control surface due to mass flow is equal to the net rate of heat and work transfer to the control volume. We can simplify this equation by recognizing that most devices studied in fluid mechanics operate under steady flow conditions, which means the amount of energy in the device is constant in time. The first term in the conservation of energy equation, which contains a time derivative, becomes 0. Additionally, most devices do not deform significantly, which removes the time dependence on the limits of integration. We will now examine the remaining terms. First, we need an expression for the specific energy, lowercase e. The total energy, capital E, is equal to the internal energy plus kinetic energy plus gravitational potential energy plus other forms of energy. These other forms of energy, which could be due to electromagnetic effects, surface tension effects, or some other effects, are usually negligible and will be ignored in this analysis. The internal energy will be represented by capital U. The kinetic energy is equal to 1/2 mass times velocity squared. The gravitational potential energy is equal to mass times the gravitational acceleration g times the elevation z. The specific energy is the total energy divided by mass, and is equal to the specific internal energy, lowercase u, plus v squared over 2, plus g times z. Now we plug the specific energy back into the conservation of energy equation. From this point forward, we will drop the subscript CV on the q dot and w dot terms in the conservation of energy equation to avoid making the equation too messy. Now let's examine the rate of work transferred to the control volume, W net in dot. We will consider three forms of work: work transferred through a shaft, work due to normal stresses, and work due to shear stresses. In fluid mechanics, devices often utilize a shaft for work transfer. For example, in a coal-fired power plant, steam flows through a turbine and interacts with a rotor, causing the rotor to rotate. The rotor is connected to a shaft, which is connected to a generator, which produces electricity. If we identify the control volume as just the turbine, notice that the shaft cuts through the control surface. The rate that work is transferred through the shaft is equal to the shaft torque T times the angular speed of the shaft, omega. Turbines transfer energy out of a control volume through a rotating shaft. Other devices such as pumps, compressors, and fans require energy input from a motor through a rotating shaft. The net shaft power into a control volume is the power required to run a pump or similar device, which we will call W shaft pump dot, minus the power extracted from a turbine, which we will call W shaft turbine dot. Fluid at control surfaces are subject to normal and shear stresses. Let's examine a small section of a control surface with area dA. Fluid flows through the control surface with a velocity v, and a small force dF acts on the surface. This force, which causes normal and shear stresses, can be broken into three components: a component in the normal direction, dFn, and two components in the tangential directions, dFt1 and dFt2. The rate of work transfer, which we call power, due to a force is equal to the dot product of the force and the flow velocity. The small amount of power, due to the normal component of the force acting on the small surface area, is denoted as dW normal dA dot, which is equal to the dot product of the normal component of the force, dFn and hat, and the velocity vector v. The normal component of the force is assumed to be the negative pressure times area dA. The negative sign appears because the pressure always points inward on control surfaces. We can determine the total power due to pressure forces on the entire control surface by integrating dW normal dA dot over the control surface. The total power due to normal stresses becomes the integral of negative P times V dot n hat times dA. Now we want to determine the power due to shear stresses or viscous effects. The small amount of power due to the tangential component of the force in direction T1 acting on the area dA is the dot product of dFt1, T1 hat, and the velocity vector v. Similarly, the small amount of power due to the tangential component of the force in direction T2 acting on the area dA is the dot product of dFt2, T2 hat, and the velocity vector v. For most devices in fluid mechanics, fluid will cross the control surface through a well-defined inlet or outlet in which the flow direction will be approximately parallel to the outward normal vector n hat. This means that the components of the velocity vector in the T1 hat and T2 hat directions are small, making the dot product small as well. Therefore, we will neglect the power due to shear stresses in this analysis. Returning to the conservation of energy equation, we plug in the expression for W net in dot, then move the integral containing pressure to the left side of the equation and multiply and divide pressure by density rho. Since both integrals on the left side of the equation have the same limits of integration, that is the entire control surface, we can combine them into a single integral. The integral can be simplified greatly by examining steady flow through a generic device that has multiple inlets and outlets and does not deform. The device is surrounded by a control surface, which is marked by red dashed lines. The control volume is inside this control surface. The direction of flow is indicated by blue velocity vectors, and the inlets are labeled 1 and 2, while the outlets are labeled 3 and 4. The direction of the normal vectors are shown in orange and point outward from the control surface. Heat transfer may occur between the device and surroundings, and work may be transferred between the device and surroundings through a rotating shaft. Notice that the integral is over the entire control surface. We can break up the control surface into multiple sections and integrate over each of these sections individually. The first section will cover the area for inlet 1. The second integral will cover the area for inlet 2. The third integral will cover the area for outlet 3. And the fourth integral will cover the area for outlet 4. We also need a fifth integral to account for the walls of the device. The dot products can be simplified by noticing that the angle between the velocity vector and normal vectors are parallel at the inlets and outlets. Recall that the dot product of any two vectors can be calculated by multiplying the magnitude of the two vectors by the cosine of the angle between them. For the inlets, the angle between the velocity vector and normal vector is always 180 degrees, which means the dot products in integrals 1 and 2 become negative v. For the outlets, the angle between the velocity vector and normal vector is 0 degrees, which means the dot products for integrals 3 and 4 become positive v. The no-slip boundary condition means the velocity at every wall is 0. We now have 4 integrals with integrands consisting of the quantity u plus v squared over 2 plus gz plus p over rho times rho v dA. We need to know how specific internal energy, velocity, pressure, and density vary over each inlet and outlet in order to solve these integrals. On the right, we have a generic inlet or outlet. There are a few possible velocity profiles that could occur. If the flow speed is very slow, or the inlet diameter very small, or the fluid viscosity very high, the velocity profile may be laminar and parabolic in shape. The velocity will be 0 at the walls and a maximum value at the center. More often, the velocity profile will be turbulent and flatter. Near the walls, the velocity drops rapidly to 0. Under certain conditions, the velocity profile will appear almost completely uniform and flat. In order to simplify the integrals in the conservation of energy equation, we make a couple of assumptions. First, we will replace the actual velocity profile with an average velocity profile that is uniform and produces the same mass flow rate as the actual velocity profile. Next, we assume that the density and specific internal energy are uniform over each individual cross-section. We also assume that the sum of Gz plus P over rho is constant over each cross-section. As we descend through an inlet or outlet, pressure increases and the quantity P over rho increases, but the quantity Gz decreases by the same amount. This result comes from analyzing the hydrostatic pressure distribution for incompressible fluids. These assumptions allow us to remove all terms from the integral except dA, and the integral of dA is simply the area A. Rho times V average times A is the mass flux m dot. So the assumptions have allowed us to convert the integral into a simple algebraic expression, the quantity U plus V average squared over 2 plus Gz plus P over rho times m dot, which has units of energy per time. If we had evaluated the integral using velocity profiles for real flows, we would find that the portion of the integral containing v squared over 2 times rho v dA is not exactly equal to v average squared over 2 times m dot. We would need to introduce a kinetic energy correction factor alpha. Alpha is a measure for how much the energy flux for the actual flow deviates from the energy flux calculated using the uniform flow approximation. For the parabolic laminar flow on the right, the value of alpha is 2. For the flatter turbulent flow in the middle, the value of alpha is typically between 1.05 and 1.1. For the uniform flow on the left, alpha is exactly 1. Alpha is often not included in the conservation of energy equation because the omission of alpha usually produces insignificant error compared to typical uncertainties in a problem, and for the rest of this derivation, alpha will be omitted. The integral over the control surface has been replaced by 4 algebraic expressions. Notice that a negative sign appears in front of the inlet terms, while positive signs appear in front of the outlet terms. We can express this equation more compactly by writing the sum of m dot times the quantity u plus v average squared over 2 plus gz plus p over rho for all outlets minus the sum of m dot times the quantity u plus v average squared over 2 plus gz plus p over rho for all inlets. To avoid making the equation too messy, we will drop the j subscript from the summations. Let's return to the conservation of energy equation and plug in the expression for the surface integral. At this point, we can define a new quantity called the specific enthalpy, which is equal to the specific internal energy plus pressure divided by density. We will denote specific enthalpy by lowercase h. Specific enthalpy, like specific internal energy, has units of energy per mass and is a property of the fluid. The conservation of energy equation then becomes the sum of m dot times the quantity h plus v average squared over 2 plus gz for all outlets minus the same quantity for all inlets equals the rate of heat transfer into the control volume plus the rate of work transfer into the control volume due to rotating shafts. In other words, the rate energy leaves the control volume due to mass flow minus the rate energy enters the control volume through mass flow equals the net rate of heat and work transfer into the control volume. This form of the conservation of energy equation for control volumes is more useful for thermodynamics applications. We will now obtain a more practical equation for fluid mechanics applications. First, we recognize that most devices in fluid mechanics have one inlet and one outlet. This means that the rate of mass flux through the inlet equals the rate of mass flux through the outlet, and we can write the mass flux as simply m dot. We will use the subscript O for outlet and the subscript I for inlet. Next, we divide the entire equation by m dot and bring the internal energies to the right side of the equation. We now have P over rho plus V average squared over 2 plus Gz at the outlet equals the same expression at the inlet minus the quantity specific internal energy at the outlet minus specific internal energy at the inlet minus net heat in per mass plus the net shaft work in per mass. Now we divide the equation by the gravitational acceleration g, and rho and g are combined into gamma. In this form, all the terms in the conservation of energy equation have units of length and are called heads. Heads make it easier to visualize energy by relating the amount of energy to a length. The P over gamma term is called the pressure head, the V average squared over 2g term is called the velocity head, and the z term is called the elevation head. These three terms are related to the total mechanical energy in the flow. The two remaining terms in the conservation of energy equation also have special names. The quantity, UO minus UI minus the net heat in per mass, divided by G, is called the head loss and is denoted with the symbol HL. This term is related to the loss of mechanical energy between the inlet and outlet due to viscous effects in pipes and fittings and is always positive. In later lessons, we will discuss empirical formulas for calculating the head loss. The net shaft work in per mass divided by G is called the shaft work head and is denoted with the symbol H shaft net in. This term is related to the gain or loss in mechanical energy due to shaft work. Let's take a closer look at the shaft work head. The net shaft work in per mass is equal to the net shaft power in divided by m dot. There are two types of devices that use shaft power to change the mechanical energy of a fluid. Pumps add mechanical energy to the fluid and are driven by motors. Power is transferred from the motor to the pump through a rotating shaft, then the pump delivers power to the fluid through interactions with the fluid. A turbine extracts mechanical energy from a fluid and is used to run an electric generator or other device. Power is transferred from the fluid to the turbine, then the turbine transfers power to another device through a rotating shaft. The net power into the fluid stream due to a rotating shaft can be rewritten as the sum of the power delivered by a pump to the fluid minus the power extracted from the fluid by a turbine. The negative sign appears in front of the turbine term because the fluid loses mechanical energy through interactions with the turbine. We also rewrite m dot as rho v average A. We separate terms and combine rho and g into specific weight gamma, as well as combine v average and A into volumetric flow rate Q. The first term, which is the power the pump delivers to the fluid divided by gamma Q, will be denoted as HP, and the second term, which is the power delivered by the fluid to the turbine divided by gamma Q, will be denoted as HT. HP is called the pump head and is related to the gain in mechanical energy by the fluid due to a pump. HT is called the turbine head and is related to the loss of mechanical energy by the fluid due to a turbine. We now have an equation for the conservation of energy for a control volume that is more useful for fluid mechanics applications. The equation is valid for steady flows with one inlet and one outlet. This equation states that the total head at the outlet is equal to the total head at the inlet minus the head loss from fluid friction in pipes and fittings, plus the head added by pumps, minus the head removed by turbines. It is important to not confuse the head loss, pump head, and turbine head with specific enthalpy, even though they use the same symbol, lowercase h. HL, HP, and HT have units of length, while specific enthalpy has units of energy per mass. Throughout this derivation, we assumed that the kinetic energy correction coefficient alpha was 1. If we did not make this assumption, the coefficient would appear in front of the velocity head terms.